Hello everyone. Today we're learning a new powerful proof technique essential for higher level mathematics. First, let's take a quick look at what we'll be covering today. Now, our journey begins with definitions, specifically what exactly is mathematical induction. Then, we'll tackle a captivating real-world problem which we've titled the Grand Pyramid Scheme Proving Exponential Growth. Imagine a new rapidly growing online scheme. On day one person recruits three others. The next day, each of those three new recruits three more people, and this pattern continues. The number of new recruits joining the scheme each day grows incredibly fast. Now, on day one, there are three new recruits. On day two, there are nine new recruits. On day three, we have 27. Our challenge is to formulate a hypothesis for the total number of new recruits after n days, and then prove this hypothesis is true for all positive integers n using a method called mathematical induction. This seemingly simple scenario will be our entry point into a sophisticated proof technique, so let's unravel it. Alright, now let's formalize our understanding. Our key definition for today is mathematical induction. Mathematical induction is a powerful proof technique used to explain that a statement, let's call it P of n, holds true for all natural numbers n, or more generally, for all integers greater than or equal to some initial value. Think of it like a chain reaction or a domino effect. There are three, sometimes four essential steps to any inductive proof. Step 1, the base case. Here, you must explicitly show that the statement P of n is true for the first value of n. This is usually n equal 1, but could be n equal 0, or any other starting integer depending on the problem's domain. Now, this proves the first domino falls. Step 2, we go to the inductive hypothesis. This is where we make an assumption. We assume that the statement P of n is true for some arbitrary positive integer k. So we say assume P of k is true. It's crucial to state this assumption clearly. This assumes that if one domino falls, the next one will fall at a particular point. Now, step 3, we go into the inductive step. This is the heart of the proof. Using our assumption that P of k is true, we must prove that P of k plus 1 is also true. This demonstrates that if any domino falls, the very next domino will also fall. This step often involves clever algebraic manipulation. And finally, in step 4, the conclusion. Once these steps are complete, we conclude by stating that since the base case is true and the inductive step shows that the implication holds by the principle of mathematical induction, the statement P of n is true for all natural numbers n. Now, for some important tips, mathematical induction is a method of proof, not a specific formula. This means you will not find it in your formula booklet. You need to understand the process. Also, for your internal assessment, mathematical induction can be an excellent tool if you've observed a pattern and formed a conjecture. Induction provides a rigorous way to prove your findings. Just make sure your algebraic steps are always meticulous and easy to follow. Now that we have a solid understanding of mathematical induction, let's apply it to our grand pyramid scheme problem. Now, first, in part 1, we're going to formulate the hypothesis. We observe that on day 1, there are 3 new recruits, which is 3 to the power of 1. On day 2, there are 9 new recruits, which is 3 to the power of 2. And on day 3, 27, so we have 3 to the power of 3. So on any given day, I, the number of new recruits is 3 to the power of I. The total number of new recruits after n days is the sum of these values. S of n is equal to 3 to the power of 1 plus 3 to the power of 2 plus etc. plus 3 to the power of n. This is a geometric series. Recalling our formula from the sum of a geometric series Sn is equal to a into r to the power of n minus 1 over r minus 1, where a is the first term and r is the common ratio. Now in our case, a is equal to 3 and r is equal to 3. Substituting these values, we get Sn is equal to 3 into 3 to the power of n minus 1 over 3 minus 1, which simplifies to Sn is equal to 3 over 2 into 3 to the power of n minus 1. This is our hypothesis. Now we'll call this statement P of n. The summation from I equal 1 till n, 3 to the power of I is equal to 3 over 2 into 3 to the power of n minus 1. Now for part 2, proving this hypothesis using mathematical induction. So our base case here gonna be when n is equal to 1. We need to check P of n when n is equal to 1. Let's evaluate the left hand side of our hypothesis. Now the sum from I equal 1 to 1 of 3 to the power of I is simply 3 to the power of 1, which is equal to 3. And the right hand side, we have 3 over 2 into 3 to the power of 1 minus 1, which is 3 over 2 times 2, simplifying to 3. Now since the left hand side is equal to the right hand side, then P of 1 is 2. Our first domino has fallen. Now in step 2, the inductive hypothesis. Here we assume that P of k is 2 for some positive integer k. So this means we assume that the summation from I equal 1 to k of 3 to the power of I is equal to 3 over 2 into 3 to the power of k minus 1. This is our crucial assumption that we'll use in the next step. Now we're gonna start with P of k plus 1. Our goal is to show that the summation from I equal 1 to k plus 1 of 3 to the power of I is equal to 3 over 2 into 3 to the power of k plus 1 minus 1. Let's start with the left hand side of P of k plus 1. So we have the summation from I equal 1 to k plus 1 of 3 to the power of I. We can split this sum into two parts, the sum up to k plus k plus 1th term. So this will be equal to summation from I equal 1 to k of 3 to the power of I plus 3 to the power of k plus 1. Now here's where our inductive hypothesis comes in. We know that the summation from I equal 1 to k of 3 to the power of I is equal to 3 over 2 into 3 to the power of k minus 1. So we substitute that in the expression. This will give us 3 over 2 into 3 to the power of k minus 1 plus 3 to the power of k plus 1. Let's do some algebraic manipulation now to get it into the form of P of k plus 1. Expand the first term, 3 over 2 times 3 to the power of k minus 3 over 2 plus 3 to the power of k plus 1. Notice that 3 over 2 times 3 to the power of k can be written as half multiplied by 3 multiplied by 3 to the power of k, which simplifies to half times 3 to the power of k plus 1. So our expression now is half times 3 to the power of k plus 1 minus 3 over 2 plus 3 to the power of k plus 1. Combining like terms, we have 3 to the power of k plus 1 into half plus 1. This will give us 3 over 2 times 3 to the power of k plus 1 minus 3 over 2, which goes down. Finally, we can factor out 3 over 2, and now this will give us 3 over 2 into 3 to the power of k plus 1 minus 1. And this is exactly the right hand side of P of k plus 1. So we have successfully shown that if P of k is true, then P of k plus 1 is also true. The domino effect continues. Now for the conclusion, we laid all the groundwork. Since P of 1 is true, and we have proven that if P of k is true, then P of k plus 1 must also be true, then by mathematical induction, P of n is true for all positive integers n. Therefore, the total number of new recruits in the grand pyramid scheme after n days is given by the formula 3 over 2 into 3 to the power of n minus 1. To get more practice and check your understanding, head over to our website to do more practice problems. The link is in the description below. Don't forget, discussion is a crucial part of learning, so if you have any questions or comments about mathematical induction, feel free to leave them below or on the website. We'll reply to them as soon as possible. Until then, keep exploring and keep learning. Thank you for watching.